Today we'll be discussing design for failure in cloud systems design. Design for failure is a core principle of the reliability pillar of cloud systems design. Subscribe to the channel and like this video for more great cloud tips. Design for failure appears in the AWS, Azure, and Google Cloud well-architected frameworks alike. The principle says you assume every component will eventually fail. You should build redundancies accordingly. Disks die, networks partition, dependencies timeout, and whole availability zones go dark. None of that is a rare event at cloud scale. So the design question is never whether a part fails. What is the real question? The question is what your system does at the moment it does. Resilience is an architectural property, not something you do later. The choices that decide it are made early in how components are connected. A synchronous call to a single database is a decision about failure. An asynchronous message to a durable queue is a different decision about failure. Both look identical on a whiteboard. They behave nothing alike at 3 in the morning. Adopting an assume failure mindset also changes what you test. You stop testing only the path where everything works. You test shift is what separates systems that degrade from systems that collapse. A single point of failure is any component whose loss takes down the system. Walk your architecture diagram. Ask what happens if each box disappears. The usual answers are a lone database, a single NAT gateway, one certificate, one region. Redundancy is the remedy, and it comes in layers. Multi-AZ redundancy runs your workload across physically separate data centers within one region. That covers power, cooling, and network failures. It is the default you should assume. Multi-region redundancy covers the rarer case of an entire region degrading. Why call it fault tolerance? Fault tolerance means the system keeps serving through a failure, not that failures stop happening. Blast radius is how much of your system one failure can reach. Fault isolation means drawing boundaries a failure cannot cross. Availability zones, regions, accounts, subscriptions, and projects are all isolation boundaries. The bulkhead pattern borrows its name from a ship's watertight compartments. You partition resources so one flooded compartment does not sink the vessel. In practice, that is separate connection pools, thread pools, or queues per dependency. If your recommendation service exhausts its own pool, checkout still has threads to serve. Cell-based architecture takes this further. It runs many small independent copies of the full stack. An incident then affects one cell's customers rather than all of them. Loose coupling is the structural defense against a failure spreading. Cascading failure is the pattern where one slow dependency exhausts everything upstream. Threads block waiting, the pool fills, health checks fail, and a healthy service is declared dead. Decoupling puts something durable between components. They can then fail independently. Queues and streams do this well. Think Amazon SQS, Azure Service Bus, Google PubSub, or KAHF-Q. Timeouts matter just as much as the queue because an unbounded wait is a resource leak. Set an aggressive timeout on every network call. Set it lower than the caller's own timeout. Cascading failure prevention is mostly the discipline of never waiting forever. A retry is the cheapest recovery mechanism you have for a transient fault. Done naively, it is also the fastest way to turn a blip into an outage. Exponential backoff spaces attempts further apart on each failure. That eases pressure on a struggling service. Add jitter, which randomizes the delay so clients do not retry in synchronized waves. The circuit breaker pattern handles the case where retrying is pointless. What happens when the breaker opens? After a threshold of failures, calls fail immediately without a network hop. That protects the failing dependency from load. It frees your own threads instantly. Libraries like Resilience4j and service meshes like ISSTO and Linkerd implement this for you. Graceful degradation means reduced service beats no service. Decide in advance which features are essential. Decide which can be shed under stress. An e-commerce site that loses its recommendation engine should still take orders. Static stability is a related and stronger idea. A statically stable system keeps working correctly when its control plane is unavailable. Pre-provisioned standby capacity rather than depending on auto-scaling during an incident. Cache configuration and credentials locally. Then, an unreachable config service does not stop request serving. The test is simple. Ask what your system does when it cannot make any changes. Automatic failover is what converts redundancy into availability. Standby capacity nobody can switch to is just an expense. Health checks drive it, and load balancers and orchestrators act on them continuously. Kubernetes restarts failed pods. Managed database services promote a replica without a ticket. Self-healing systems handle the routine failures with no human involved at all. Recovery time objective is how long you can be down. Recovery point objective is how much data you can lose. Backups with restore drills serve a relaxed RTO. Warm standby or active-active serve a strict one. Untested backups are not a recovery strategy. They are an assumption. Chaos engineering is how you find out whether any of this works. It is disciplined experimentation on a system to build confidence in its behavior under turbulence. You begin with a steady state hypothesis, a measurable definition of normal. Then you inject a realistic fault and predict that steady state holds. Failure injection covers terminating instances, adding latency, dropping packets, and exhausting CPU or disk. AWS Fault Injection Service, Azure Chaos Studio, and the open source Litmus Chaos and Chaos Mesh all do this. A game day is the human version. It is a scheduled exercise where you break something and practice responding. What does resilience testing actually find? Resilience testing finds the gaps that reviews miss, usually in runbooks and alerting rather than code. Learn more at systemsarchitect.io. Like and subscribe to the channel and follow the playlist. The obvious return is availability, since redundant systems survive events that would otherwise page everyone. The larger return is a shorter mean time to recovery, because recovery paths are automated and rehearsed. Reliability improves in a way customers actually notice. Partial degradation replaces total outages. Operations gets quieter, since self-healing absorbs the failures that used to be pages. Security benefits from the same posture, because assume breach and assume failure ask the same question. There is even a cost argument. A well-understood failure mode is cheaper than an unbounded incident. Every layer of resilience costs money, latency, and complexity. Multi-region active-active can double your infrastructure bill. It also forces you to confront data consistency directly. For an internal tool with a 4-hour RTO, backups and a documented restore are the correct answer. Match the investment to what the outage actually costs, not to what is technically impressive. Complexity is its own failure mode, and circuit breakers, retries, and failover logic can misfire. Chaos engineering is premature before you have basic observability. Breaking a system you cannot measure teaches you nothing except that it broke. Start with multi-AZ redundancy, timeouts, and tested backups, then earn the advanced patterns. Design for failure means assuming every component eventually breaks, then building redundancy, isolation, and automated recovery so that no single failure becomes an outage. Its mechanics are eliminating single points of failure and containing the blast radius through bulkheads and loose coupling. You protect callers with timeouts, backoff, and circuit breakers. You degrade gracefully instead of collapsing, and fail over automatically against clear RTO and RPO targets. Start with multi-AZ redundancy and tested restores. Add graceful degradation and self-healing as the stakes rise. Use game days and chaos experiments to prove the design works before production proves it does not. Thanks for checking out this video, and like the video and subscribe to this channel. Find a lot more articles and guides on both systemsarchitect.io and codeguides.io. Again, that's systemsarchitect.io and codeguides.io.